Good morning, everyone. Welcome to the third session of the workshop, Nonlinear Structural Mechanics using Python. So in the last session, we had gone up to the assembly of stiffness matrix for a bar element. So we started off with, we initially started with defining the elements, bar elements, their degrees of freedom and the corresponding forces. We said there is something called the stiffness matrix for an element that relates the forces to the displacements at the ends of the element. And this is for one element. We are also interested in constructing this force displacement relationship for an assembly of several elements. And in that process, we are expected to uh, respect certain conditions, such as one is compatibility, that the connected nodes have to have the same displacements from either of the two elements. And the other condition is um, the sum of all element forces at that connected node should be equal to the externally applied force at that node. So given that our assembly satisfies these conditions, you get what? You get a global stiffness matrix which relates the global forces applied on the nodes to the global displacement degrees of freedom U1, U2, and U3. And this matrix is called the global stiffness matrix. So we saw in the last session we wrote a small code to make the assembly of this global stiffness matrix, which was the most technical part. And then we solved the full system for the unknown displacements. So this was the homework assignment. You can work on it. Yeah, I think I don't have to discuss the answers here, solution here, because it is very straightforward. You can just do it in the similar manner to the problem that I solved, the problem of two bars connected at and you're applying a midpoint force, right? So did you face any difficulty? If you have any doubts, you can ask me now. So because today we'll be entering the next part of the we'll enter the next part, which is the direct stiffness method for beams. So we'll be going from 1 degree of freedom per node to 2 degrees of freedom per node. So before getting to that point, you can tell me if you have some problems, you have any issues, or if everything is clear, we can go ahead. If you have any doubts in the bar element assembly, in bar element problems, you can ask me. If not, we'll just proceed with today's content. Just a minute.
Yeah.
Okay. I think we can go ahead. So okay. Okay. So the coming to the idea of a beam element stiffness matrix, right? So uh, yeah. So think about it. When we had the bar element, we had two nodes and 2 degrees of freedom, right? So in the bar element, we had something like this. Yeah. So either we call it the bar element or the axial force member. You had a node here, you had a node here. All forces are assumed to act axially in this direction. And it doesn't have any transverse degree of freedom. You're only looking at the axial degree of freedom. So it has got 2 degrees of freedom, U1, U2, and correspondingly it has two forces, which is the force at the first node, F1 and F2. So therefore we had a relationship between these two. So the force at node 1 can depend both on displacements at 1 and 2, nodes 1 and 2. Same for force 2. So you have a certain relationship between the forces and the displacement. Now, analogous to it, don't worry about how it comes. But if you look at a beam element, so beam element, all of you know, beam is something that resists transverse loads by flexure. So beam is something that resists transverse loads. A bar element is something that resists axially applied forces. So a beam element resists transverse loads by flexure, by undergoing bending or flexure. So in an axial force member, it resists axially applied loads by undergoing extension, right? Extension or shortening. And beam element resists transversely applied loads by undergoing flexure or bending. So, so all of you know what a beam is. You know the conventional Euler-Bernoulli beam. So you have a set of relationships. You have all the you have the relationship between the moment and the curvature. So m by ei, you call it as the curvature. And then you say the strain is under certain assumptions. You say the strain is y by rho, right? Where y is the distance from the neutral axis. So the strain in a fiber at a distance y from the neutral axis is just y multiplied by the curvature, or y divided by the radius of curvature. And then you have the relationship stress as it is E times y by rho, which is nothing but my by I, right? So, and m itself depends on some function of the applied transverse loads. So let me call the transverse loads P. It is some function of the applied transverse loads. So you take, you're applying loads that are perpendicular to the axis of the beam. And what the beam does is it undergoes a certain process called bending. So the moment induces a curvature in the beam, and that curvature causes the fibers oriented along the axis to stretch, and that induces an axial strain. So you're applying a transverse force, and that induces axial strains. Axial straining of fibers. So this is what a beam basically does. Now let us see what a beam element would relate, right? So what are the differences? One, the forces are not just axial. Second thing, if you can have transverse forces. Say suppose when you have transverse forces, you say if it has to be in equilibrium, you have to apply say a force P1 here. And this at this point, if the beam has to be in equilibrium, it has to have an equal and opposite force P2 here. Right? So, but this alone is not enough to keep the beam in equilibrium, because this is a pair of forces that are separated by some distance. So they will introduce a net moment which will cause the beam to rotate. So it cannot, for moment equilibrium, it requires some moments in addition to this. So it has got some moments, say M1, M2, to keep it in equilibrium, right? So for a beam element, it is not enough to have just 1 degree of freedom per node. The reason being, for if you just have 1 degree of freedom, so 1 degree of freedom will correspond to a force, one force per node. But one force per node by itself is not enough to keep the beam in equilibrium. So you can think of, so you need a moment. Therefore, energetically complementing to the moment, you need you need a rotation. So, so it's like you need components that are conjugate to each other. For example, force multiplied by a displacement gives energy or work done. Similarly, moment multiplied by rotation gives a certain energy. So these two. So if you require a moment, then you need a rotational degree of freedom. Similarly, if you have a force, you need a displacement degree of freedom. This is not so when you take a proper finite element course, you will see more details onto why you need a rotational degree of freedom. So that actually comes from the degree of the governing partial differential equation. But you don't, we don't need to get to that point now. You can just understand it in the way that what is the need for 2 degrees of freedom. So the correct, perfectly acceptable reason is that you have the governing equations of a so you may come across this later, but the governing equations of a beam are 4th order. So it has got two two primary variables. So when you write down the weak form, you'll be able to eliminate 2 derivatives. So when you write down the weak form, you'll be able to eliminate 2 derivatives, and the resulting equation will have 2 primary variables, which is the lateral deflection itself and the derivative of the lateral deflection. So this derivative of the lateral deflection, we call it the rotation under small strain, small deformation conditions. So so any finite element or any element that is attempting to model beam will have to ensure that the rotation field is also constant across elements. So that is the reason we actually have 2 degrees of freedom per node. So it is to ensure certain continuity of the assumed solution field. But from a structural viewpoint, for the purpose of this workshop, you can also understand it this way, that you cannot keep a beam in equilibrium by the action of forces alone, nodal forces alone. So you also need moments. But if you have moments, correspondingly, you need its conjugate, which is rotation. So beam element has got 2 degrees of freedom per node, which is the displacement, the lateral displacement and the slope. So these are the conjugate quantities. You have a rotation θ1 and conjugate to it you have a moment m1. You have a rotation θ2 and conjugate to it you have a moment m2. And with respect to the central line of the beam, you have the points could be displaced by v1 and v2, which are conjugate respectively to f1 and f2. So what we intend to get here is we have got 4 degrees of freedom per node. So what we want is we have, say, f1, m1, f2, m2. These are the 4 degrees of freedom. So, and the conventions you can note it. F1 and F2 are positive upwards, and M1 and M2 are positive and they are taken in the counterclockwise direction. So these have to relate to some 4 unknowns, which are V1, θ1, V2, θ2. So you have 4, this is a 4 cross 1, this is 4 cross 1. So you need a matrix that is 4 cross 4, which relates. And this is the beam element stiffness matrix. Right? So the only thing that changes in our code will be the beam element stiffness matrix, and the rest, everything else is the same. So the procedure will still start with the problem formulation, and then you will carry out assembly. And in the assembly, you will be calling the beam element stiffness matrix, and you will also have to put them together. So you call the beam element stiffness matrix, assemble it, then enforce the boundary conditions, invert and solve. So the same code with some slight modifications can be used for the beam elements. So I think we can get started. So first task here will be to derive the beam element stiffness matrix. And if you derive it, this will be your final form, right? So how do you derive it? So some of you have taken matrix structural analysis and or finite elements. So how do you, because there are many ways to do it. In finite elements, it's done using shape functions. In matrix structural analysis, there are some other ways to do it. And there are also certain energy methods. So how do you do it? Maybe you can list the methods. This is what I'll be doing. So this is one way.
Flexibility matrix method, stiffness matrix method.
Okay, so how do you get the flexibility matrix first?
Flexibility by allowing the motion along that coordinate and restricting all other.
That is the stiffness matrix method. So if you allow the displacement, so if you say you apply a unit displacement along this coordinate, and you restrict everywhere, you restrict the all other degrees of freedom, that is For a unit displacement, you're checking what are the forces induced. So that is the stiffness method. So that's basically the definition of stiffness matrix. That is fine. So you apply unit displacements at a degree of freedom and find the forces, right? But how do you find the forces? That's the problem, right? Suppose you allow this has got 4 degrees of freedom. So suppose I want to first apply just V1. I'll apply V1 and keep the rest fixed. So it will be something like this. So we first apply V1 is equal to 1, theta 1 is equal to 0, theta 2 and V2 are 0, and then you can measure all the forces and moments that are induced by this. But this itself is a highly indeterminate problem. It's a statically indeterminate to the degree of 2. No, it's statically indeterminate to the degree of, actually, yeah, it's actually statically indeterminate to the degree of 2 in plane. If you remove the condition of, if you remove the effect of axial forces, it is statically indeterminate to the second degree. How do you solve this problem? So once you apply unit force here, you will need to get these problems, right? You need to get all the reactions, and equilibrium equations are alone not enough to do it. So same applies to flexibility. So in the case of flexibility, it is you look at a structure like this, and then you apply the force corresponding to one of them, and you measure the displacements. So this is like apply unit force, displacements. Okay, so these two are acceptable methods, and the difficult step is that how do you find the forces, because it's indeterminate. And you can use any of the indeterminate method analysis. Then anything else using? So how do you get the forces directly? You think of any technique in structural analysis which gives you the forces directly? So this image itself should tell you something. The forces here will be something like 6Ci by L delta square. 6Ci by L square delta, something like this. Have you seen? And this particular term comes in certain method called slope deflection method. Right? That is one displacement based analysis method where you can apply a displacement and directly the moments and the forces. Right? You can do that. Then as I said, the other method is the FE method, where you construct a weak form, then discretize it using shape functions. And this you can integrate to get the stiffness. Right? So this is the most powerful method. It's not just limited to beams. You can do it for anything. So this is one thing. So from the governing equation, get a weak form, which is in the form of an integral. And that is still continuous. So you need to discretize using some assumed shape functions. Then you integrate it, so you get some stiffness matrix. So this is very powerful. Even in cases where we can't derive the exact stiffness matrix, you can get some approximations. So this is very powerful. And anything else using energy techniques, you can do that. Principle of minimum potential energy. There are ways to do it. Then principle of minimum potential energy or stationary potential energy, PSP. You can do that. And yeah, there are a variety of methods to do this. So since we have both civil and mechanical audience, let me not go through these because these involve certain advanced structure analysis techniques. You need to know about some. Yeah, so the slope deflection equations themselves are not obvious, right? They have to be derived from something. Similarly, the method of consistent deformation also involves solving simultaneous system of equations. So maybe let's look at some energy method, right? So all of you should have seen. Okay, we have. Okay, let me. So all of you should have seen some kind of Castigliano's theorem, right? Some form of Castigliano's theorem. We'll use that and derive the coefficients, right? So think of it this way: we have a we have a beam. So this is based on this is quick and fast. So you can say it is flexibility based method. So suppose this is a beam element. This is node 1 and this is node 2. And correspondingly, you have displacements V1, theta 1, V2, and theta 2. So V1 and V2 are displacement components, and theta 1 and theta 2 are rotation, and you can call them all together as generalized displacements or generalized coordinates. Generalized coordinates or displacements. You can also say this is generalized coordinates or displacements. You don't want to say it's a displacement rotation every time. So even if you have a temperature field, you can actually call it a generalized coordinate or displacement. Right. So so we want to get the relationship between these and the corresponding forces. You have force F1, M1, F2, M2. This is node 1, node 2. We want to be able to relate these two. So let's take one at a time. Suppose we set V1, sorry. Suppose we set V1 is equal to theta 1 is equal to 0. What do we get? We get a cantilever beam with what applied? With a force F2, M2 applied, and this will result in some displacement. This will result in a displacement V2 and theta 2. Right? So how do we find V2 and theta 2? Directly from this? You have certain formula, but systematically, how do you do it? So F2, you know, it is given F2, you know, V2 is F2 L cube by 3EI, and given M2, you know, theta 2 is M2 L square by, sorry, M2 L by 2 EI. M2 L by EI, and V2 due to M2 will be certain. Okay, we'll do it. Right? Why do? So you have this. So first, let us write down the energy of the system, the strain energy of the system. So the strain energy of the system is what? So you ignore the components from the axial force and shear. So you say bending strain energy is strain energy due to bending. That's important, right? The strain energy due to bending. What it is? It is integral 0 to L. What comes in here?
M square dx by 2EA. So
M square by?
M square by 2EA.
Maybe it's breaking. Your voice is breaking a little.
M square dx by 2EA, sir.
Okay. This is correct. How do you get it? You take, say, you take an infinitesimal segment of the beam that has bent. So this may be at a distance x from the support, right? X from some assumed origin. And say the length of the beam is dx, right? So this length is dx. So this rotation is what? So this point has rotated by some amount. Let us call it d theta. And say this at this distance x, it is subjected to a moment of m of x, right? So what is the incremental work done? So the incremental work done in this case will be it's not the incremental work done, it's the work done in the small beam. So it's dw, not delta w. So let me. So I have this in this small section of the beam, what is the work done? So this, so the work is done by this moment, right? So it is m d theta. Yeah, you can say moment is complementary to the rotation, so it is just m d theta. And if you consider linear elastic body, if you consider it to be linear elastic body, it is half of this. So if you go from m theta, the work done by this as the force rises in a static manner from 0 to this point is half of m theta. So this is theta and this is m. It is area of the triangle, which is half. Basically the moment is caused by this rotation, and the rotation is caused by the moment. So when the rotation is 0, moment is 0. So you cannot multiply it directly. So if the moment has been acting through the rotation, moment was pre-existing, then it's just m d theta. But the moment rises from 0 to d theta in a linear elastic fashion. So the area under the curve is half of the triangle. Therefore, the strain energy or the work done by this moment is half of m d theta. What is d theta? D theta is this rotation, and d theta is nothing but what it is? Dy by dx. Sorry, it's the differential of, right? Theta is dy by dx. So d theta is a small quantity like this. So it is nothing but d square y by dx square dx. But what is d square y by dx square? From beam bending theory, it is m by e. Yeah, it is the curvature. It is nothing but m by e when you integrate it through this thickness and stuff. So you get something like this. Therefore, the incremental work done, sorry, not the incremental, the small work done in this section of the beam over a section dx is nothing but half m by e dx. So net work done will be equal to the strain energy. So it is integral 0 to L integrated. So it is m square by 2 ei dx. So this is what we have here. Now we are just left with the task of finding what is m of x. What is m of x for this beam? I'll give you the origin from the right hand side. Let's take x like this, just for simplicity. What is m of x for this beam?
F2x plus M2.
M2 plus
F2x.
yes. So yeah, you'll have a plus or minus sign depending on which direction you take. But anyway, you're squaring it, so it doesn't matter. So just in this form, if you take sagging moments as positive, you'll get a plus. If you take hogging moments as positive, you'll get a net minus, right? You'll get a minus multiplying the entire thing. But anyway, you're squaring it, so the sign doesn't matter. So now just what do you have? You have integral 0 to L 1 by 2 ei m2 plus f2x square dx. Expand the summation, you get some terms like this. So let me bring the 2 ei to the left. So it is 2 ei u is equal to integral 0 to L m2 square plus 2 f2 m2x plus f2 square x square dx. Do the integration, you get 2 ei u is equal to what? You get this m2 square L, right? This is constant. Plus you have a 2x here, so that gives f2 m2 L square. Plus here you get f2 square L cube by 3. Is that okay? You get the same answers. You get the same terms. Yeah. So just so we have an expression for the strain energy in terms of the forces, right? So you have this is fine. What do we do next? I want to get V2 and theta 2. What is the relationship between theta 2 and this? Sorry?
du by dm2 will give theta and du by df2 will give Deflection, sir.
Deflection, yes. So Castigliano's second theorem states that the deflection, the load point deflection let us call it delta due to a load P for a linear elastic structure is obtained as where U star is the complementary strain energy. Which is, how do you define the complementary strain energy? It is dP, delta of P dP from 0 to the point P, right? So this is basically the area of the stress area above the stress strain curve. You have the strain energy up to this point. This can be delta, this is P. So this area, take this area and then differentiate it with respect to the applied load P. So you will get the load point deflection delta. And for a linear elastic structure, this curve is a straight line. So it's the diagonal of a rectangle, and the diagonal of a rectangle divides it into two equal areas. You can always replace the complementary strain energy by the actual strain energy U. Now, as one of you pointed out, V2 is dou U by dou F2. So do the derivatives differentiation. What do you get? First term will not contribute. It's just dependent on M. Second term will contribute M2 L square by 2 EI. And the third term will contribute F2 L cube by 3 EI. So you get a 2F2 and the 2 gets cancelled with the 2 outside. So you get this. Similarly, what do you get for theta 2? Theta 2 is dou U by dou M2. And in that case, what do you get? So first term will contribute. It is M2L by EI plus F2L square by 2EI. Now can we arrange it in a matrix form? So now we have a relationship between V2 theta 2 and M2 F2, right? Let's put that. So on the left hand side, we have V2 theta 2. You have some matrix. We'll populate the matrix soon. And on the right, you have F2 M2. So can one of you tell me the coefficients? What is this? What relates F2 and V2?
LQ by 3 EI, sir.
Okay. M2 and V2?
L square by 2 EI.
Theta 2 and F2?
L square by 2 EI.
Okay.
L by
And
EI.
yes. So what is this matrix called as? Stiffness, flexibility?
Stiffness, a flexibility matrix, sir.
Yeah, this is a flexibility matrix. Because corresponding to applied unit, so these are the displacements that will be produced if you set F2 equal to 1, M2 equal to 0. These are the displacements that will be produced. And if you set F2 equal to 1, sorry, what did I say? If I say F2 equal to 1, M2 equal to 0, the first column will be the displacements that are produced. And if you set F2 equal to 0 and M2 equal to 1, the second column will be the displacements that are produced. So corresponding to unit forces, these are the displacements that are produced. So this is the flexibility matrix. Next, what do we do? Next, so this is only half of the job is done. So we only have a relationship between V2 theta 2 and F2 and M2. But our goal is to get a relationship between all four components, right? We want to get Okay, we want to relate all four components of, we want to relate V1 theta 1, V2 theta 2 to M1 F1, F2 and M2. So what do we do? Let's look at the force diagram once again. We have F1, F2, M1 and M2. What are the equilibrium equations here? So first we have got one pair of relationships between F2 theta, the second node. At the second node we have got one pair. But what are the equilibrium equations for this? This in general is not in equilibrium. So if it has to be in equilibrium, the net vertical forces should be 0. So F1 plus F2 should be equal to 0. And for moment equilibrium, suppose I take moments about the first node, what do I get?
M2 plus F2 into L equal to 0.
No,
Equal to M1.
no. Let's look at the signs. M1 and M2 are in the same direction, so it just gets added up.
Plus M1.
Yeah, right. So yeah, you should be careful. It's fine. So this F1 will not contribute to the moment at this point, but the moment itself, moment at that point will obviously contribute, right? So F1 will not contribute. Now just this can be written in a matrix form. So we already have a relationship. We have the forces at M2 and forces and displacement at node 2 are related. Can we get the forces at node 1 in terms of node 2? So that's the question. Can we get the forces at node 1? Again, these are called generalized forces. You call both forces and moments as generalized forces. I don't want to write everywhere forces and moments at node 1 in terms of node 2. Can we do that? Yes. So use these relations. You get F1 is equal to minus F2 and M1 is equal to minus F2L minus M2. So you can add a 0 M2 here. Now what do you get? Now can you write it in a matrix form? Yes. F1 M1 is equal to what? Something relating to F2 M2. So the coefficients of this are minus 1, 0,
Minus 1, minus 1.
minus L, minus 1. So yeah, it's not minus 1, it's minus L. So what this says is that once you get in any statically admissible system, the displacement can be anything, but in any statically admissible means the forces are in equilibrium, right? Statically admissible means it obeys the static equations of equilibrium. Therefore, the forces are obeying the equations of equilibrium. So it is statically admissible. So in any statically admissible system, regardless of what the displacements are, this should obey. What that means? What that means is that okay, so let's call this equation set 2. Right, let's call this equation set 2 and let us call this equation set 1. Now this is a relationship between displacements and forces. We want force displacement relationship, so we need the stiffness matrix. So what to do? We just have to invert it, right? So before we invert it, let's just take some things common. This L cube by 3i can be taken out. L cube by EI can be taken out. So I have from 1, I have V2 theta 2 is equal to, let me take L cube by EI out. And inside the matrix, I'll be left with 1 by 3. What do I have? 1 by 3, L by 2, L by 2 and 1 by 3, L by 2, L by 2 and L square by 1. Yeah, L square. So F2, M2. Now let's call this matrix as S. So you have V2 theta 2 let's take this to the other side. EI by L cube P2 theta 2 is equal to some flexibility matrix times F2 M2. I can multiply by S inverse on both sides. So I get EI by L cube, which is a scalar, times S inverse V2 theta 2 is equal to F2 M2. And this S inverse multiplied by this entire thing is called the, so this entire thing is together called the stiffness matrix, right? Because it's a reduced stiffness matrix. It relates the forces to displacements. Now, what is our task? We just have to invert this matrix. So what is the inverse of this matrix? The shortcut for 2 cross 2 matrices. How do you invert a 2 cross 2 matrix?
1 by determinant into adjoint.
Okay, so what is determinant of S here?
L square by 3 minus L square by 4.
Yeah, so it is L square by 12. Okay. So S inverse is?
And 1 by 12 by L square into L square minus L by 2 minus L by 2 1 by 3. So
Yes, perfect. So you swap the diagonal entries and multiply the other non-diagonal entries by a -1. So that gives the inverse of a 2 cross 2 square matrix. Now, fine. So we have got the inverse. So we say F2 M2 is equal to 12 EI by, okay. Now there is a slight issue. So you have an L square here and okay, let it be. You have a 12 EI by L power 5 and inside you have L square minus L by 2 minus L by 2 1 by 3. Something is off. This is fine. L cube. Okay, this is the problem. So it's a mess. So this is L cube by 3A. So here it is L square
1
by
by
2
2
U.
L.
Yeah, it's 1 by 2L. Yeah, that's what I felt. And this is 1 by L square. So determinant is wrong. Sorry about this. Inverse is wrong. Yeah, I'm taking L cube commonly out. So L cube is in the numerator. So this lacks a degree. So it is 1 by 2L. 1 by 2L. 1 by L square. Yeah. Now tell me what the determinant is. Determinant is 1 by 3 L square. Just the L square from numerator goes to the denominator. 1 by 4 L square. So this is 1 by 12 L square. Perfect. Sorry. This is the determinant, right? This is 1 by 12 L square. It's not this. Yeah. This is the determinant. So the inverse is swap the
1
diagonal
by
entry.
L square.
Yeah, 1 by L square.
Minus 1 by 2L. Minus 1 by 2L. And 1 by 3, sir.
By 3. Perfect. And then we have a 1 by determinant of L, which means you're multiplying this by. So yeah. So you're multiplying this by 12 L square. So determinant of S is 1 by 12 L square. So you multiply this by 1 by determinant. So you get a 12 minus 6L minus 6L and 4L square. So this is the inverse of the flexibility matrix. So therefore this This I can write it as so this relation can be written as I'll write it in this form. F2 M2 is equal to EI by LQ and S inverse is 12 minus 6L minus 6L 4L square V2 theta 2. Now what about F1 and M1? F1 M1 from equation 2, they are given as we had something right minus 1
0 0
minus L
minus L minus 1 F2 M2
F2 M2.
F.
Now can you substitute for F2 M2 from this? Yes. So you can write this as you can take the EA by L cube out. That's anyway scalar. Minus 1 0 minus L minus 1. Then you have a 12 minus 6L minus 6L 4L square. And then you have V2 theta 2. Now what is it giving us? So you get EI by LQ. F1 M1 is EI by LQ. So first one is minus 12. Sorry. Yeah, minus 12. Second, this will, and then you had 6L square. Sorry, 6L minus 0 into 4L square. So it is just 6L. Then you get minus 12L plus 6L. So it is a minus 12L plus 6L. So it's minus 6L. And you have 6L square minus 4L square, which is 2L square. This is multiplying B2 and theta 2. Now combine these two equations. Combine this equation, this equation and this equation.
So the matrix is not symmetric. F1 M1 equal to this last matrix. Why it is not
the last
symmetric?
It is not symmetric. So the reason is, oh sorry, what happened to the okay, yeah, fine, it's back. So the reason the last, so that's a good question. So one thing you need to notice is that this matrix is symmetric because these two are corresponding degrees of freedom, right? F2 V2 M2 theta 2 are corresponding. So F2 is the displacement.
Yes, sir. Yes,
sorry,
sir.
F2
corresponding force corresponding to that displacement.
Yes. Here you don't need
Here
to have it
essentially. Yes, sir.
Yes.
Yes, sir.
So this follows from Maxwell's reciprocal theorem. So you have that it says that you have a system of forces acting on you have a system of forces doing some work on another system of displacements, and you say the system of forces work done by this set of forces on this displacement, and this set of forces on this displacement have to be equal. So that's Maxwell's theorem. So which means when you apply a unit load here and measure you apply unit force here and measure the moment, or you apply unit rotation and measure the force, those two have to result in the same values. But here you are measuring at different point. You're applying displacements at node at 1 and you're measuring it at, you're applying displacements at 2 and you're measuring the forces at 1. So they don't have to be symmetric. That's the idea.
Yes,
yeah. So this is fine. So this, so hope you get it. Now, what do we totally want? We want F1, M1, F2, M2. This is the net left-hand side we have. And this should be equal to, right now we don't have all the 4 degrees of freedom. We just have V2 and theta 2. But that is still okay. So this is 2 cross 1. This is 4 cross 1. And whatever relates these two should be 4 cross 2. And what are they? Just append the two matrices together. Mix. We zoom out a little so that you can see. Yeah, just append one matrix after the other, right? So you get F1 is equal to something my times V2. So it is minus 12L, minus 12, 6L, minus 6L, 2L square. This is the relationship between F1 M1 and V2 theta 2. And what about F2 M2 and V2 theta 2? This is the relation, right? So put it here. 12 minus 6L minus 6L 4L square. So we got half of the matrix. Which half of the matrix?
is minus 6L. A12.
A12 is not minus 6L. A12 is 6L.
Yes.
It's relating F1 to V2. F1 to theta 2. So it is 6L. Yeah. So we got half of the matrix. We got which half of the matrix? We got the right half of the matrix, right? The full stiffness matrix relates V1 theta 1, V2 theta 2. And the first two columns of this matrix will multiply with V1 and theta 1. Right? First two columns of the matrix will multiply with V1 and theta 1. The next two columns will multiply with V2 and theta 2. And we have only the coefficients corresponding to V2 and theta 2. So we got the right half of the matrix. So this is the right half. Right? So that is fine. That's good enough. Now let us just fill in the matrix. As we get it, let us just fill in the matrix. So we'll fill the right half with this. Minus 12, 6L, minus 6L, 2L square, 12, minus 6L, minus 6L, 4L square. Now look at it this way. Can you get these coefficients? Now look at the full matrix. It actually relates V1 theta 1, V2 theta 2. And on this side it has F1, M1, F2, M2. Now this, if you see, what are these set of coefficients relating? This set of coefficients are relating the forces F1 and M1 due to displacements V2 and theta 2. Right? Now the work done, so now you can use Maxwell's reciprocal theorem. So the work done by the system of forces F1, M1 on this V2 theta 2 should be equal to the work done by the forces F2, M2 on V1 theta 1, right? So this the full element stiffness matrix has to be symmetric. So what will this element be? So this and this has to be symmetric. So what will come here? Right, this is 3, 1, the element 3, 1, and that should be equal to 1, 3, right? So this will be minus 12. You get it?
Yes, sir.
Right. So the idea is this matrix has to be symmetric because of Maxwell's theorem. When you have just V1 theta 1 and this F1 M1, this is not the full work done. But when you have but when you have this entire system F2, M2, F1, M1, this is the full matrix. This matrix has to be symmetric. The full stiffness matrix has to be symmetric because it shouldn't matter whether you are applying, whether you're keeping this fixed and measuring this, or you're keeping this fixed and measuring the other one. So this will be A31 will be A13, A32 will be A23,
minus 6L,
A41 will be A14,
6L,
and A42 will be A24. So now we got 3/4 of the matrix, right? We only want this part. We only want this part, which is we only want this submatrix. Now I would say look at this relationship. Now set V2 equal to theta 2 equal to 0. What happens? If you set V2 equal to theta 2 equal to 0, you get F2 M2 am I audible? There was a connection issue, I think.
No, sir. F2
Yeah,
M2
okay.
was
So
audible.
okay. So F2 M2 is equal to what? When you said V2 and theta 2 are 0. So V2 and theta 2 are 0. So it depends only on V1 and theta 1. What do you get here? What relates F2 to V1? Minus 12, right? So in this entire system, you just set V2 equal to theta 2 equal to 0. So then you reduce the system. So for I'm saying just set V2 equal to theta 2 equal to 0. So you get some same stiffness matrix multiplied by V1 theta 1 0 0. If you do that, so whatever is multiplying the second, these two columns are multiplying this one, right? So these two columns, it doesn't matter what the coefficients are. Only this will contribute. So F2 is equal to minus 12 V1 minus 6L theta 2 plus 12 V2 minus 6L theta 2. But V2 and theta 2 are 0, so these two will not contribute. So you're left with just minus 12 V1 minus 6L theta 1. Similarly, M2 is equal to 6L V1 plus 2L square theta 1. Is that okay? Basically, this matrix will just appear here.
I had a connection issue.
Oh, okay. So this is fine. So I think this should be okay. So the matrix that relates the forces in the second node to the displacements in the first node is exactly this matrix. Then you can okay, so this you call it as equation 4. Now this is a set. Suppose these forces have to be in equilibrium. If it has to be in equilibrium, we already have a relation that F1 M1 is equal to what? This should be -1 0 minus L minus 1 F2 M2, right? So everywhere there's an EI by L cube. There's an EI by L cube everywhere that you have to. Sorry, it's not here. So these equations hold always, regardless of whether you keep V2 node 2 fixed or node 1 fixed. This has to be always satisfied. F1 M1 should be always minus F2 minus LF2 minus M2. If this is not satisfied, then the beam is not in equilibrium. So this is always satisfied regardless of whether V1 is equal to 0 or V2 equal to 0 or any other boundary conditions. So right now we are looking at cantilevered beams. Even if you have simply supported beam or any boundary condition fixed, this relation cannot be violated. So let us get F1 M1 from this equation. What do you get? So you get F1 M1 for this case 2. Let's call this case 2. For this case, F1 M1 is -1 0 minus L minus 1. We'll take the EI by L cube outside. Multiplied with -12 minus 6L 2L square. What is this equal to? It is EI by L cube 12 6L. Then you get a 12L minus 6L, which is 6L. And then you get a 6L minus 2L square, which is 4L square. And okay, you have a V1 theta 1 here, right? So this is equal to V1 theta 1. So this is the relationship between F1 M1 and V1 theta 1. Now plug this back into our stiffness matrix. So what are missing here? These are the missing coefficients. These are the missing coefficients. What relates F1 and V1 here? F1 and V1 are related by 12 EI by L cube. So you have a 12. Then you have theta 1 and F1 are related by 6L, right? So you have a 6L. V1 and M1 are related by 6L. And theta 1 and M1 are related by 4L square. So finally, the stiffness matrix turns out to be this EI by L cube 12 6L. So this is our stiffness matrix. And you can check it matches with this. It's EI by L cube 12 6L minus 12 6L, 6L 4L square minus 6L 2L square, minus 12 minus 6L 12 minus 6L, and 6L 2L square minus 6L 4L square. So yeah. So we got the beam element stiffness matrix. Now we can start coding. So we have spent about an hour into this. Yeah, we shouldn't have spent this long. But is there any doubt? So so this procedure can be used for deriving the stiffness matrix for anything. So start with some energy technique or some method to get the displacements for a statically determinate system. You get the flexibility matrix for the reduced system. So what is the flexibility matrix for the reduced system? Something that relates the forces to the displacements. For unit forces, what are the displacements that are generated? That is the flexibility matrix for the reduced system. But you also have equilibrium conditions, which says that under any boundary conditions and loading, these conditions have to be satisfied. That the force at node 1 should be the negative of force at node 2, and the moment at node 1 should be the negative of moment at node 2 plus the negative of F2 times L. So these have to be satisfied for any statically admissible system. Therefore, you can get the forces at node 1 in terms of the forces at node 2. But forces at node 2 themselves can be obtained in terms of the displacements at node 2 by inverting this flexibility matrix. So you get this relationship. Then use the conditions of equilibrium to get a relation between F1, M1 and V2 theta 2. So that will fill half of our stiffness matrix. Then our stiffness matrix for an element has to be symmetric. So this half, the lower half of this left half can be obtained just by symmetry conditions, right? Then what will be left is just one part. How do you get that part? Again, use the equilibrium equations, because this piece of information actually relates V1 theta 1 to F2 M2 when V2 and theta 2 are 0. So again, when you get F2 and M2, you can get F1 and M1 just by using the equilibrium conditions. Therefore, multiply this equilibrium matrix with the reduced stiffness matrix. So you get this, the remaining 4 coefficients as well. Then put them all together, we have got the beam stiffness matrix. So this may seem very lengthy, but once you get this, the coding part is actually easy. Yes. So okay. So these are some programming problems. We'll now start coding them, right? So you can go to this, not this. Any doubts here? I'll.
No, sir.
Okay. So I don't know if I have uploaded it on Classroom. Okay, so this so this is the skeleton, code skeleton for the beam problem. I'll upload it to our drive. It's here. So this is code skeleton. Yes. Topic will be codes. So this should appear here. You can open this in a, you can open it and make a copy, right? You can make a copy of this I said it. So you can say file, save a copy in drive and name it in a different, name it something different. So you can start coding with me. Right. So yeah. So you can name it with something else. You can say, put your name. Yeah. But I will actually work on this, but you people work on the copy. Okay. So I hope you have done that. Yeah, you may need some time to just click it, open it in Google Colab, and then make a copy. Then let me know. We'll start coding here.
Yes.
Done. Okay. Others? Anybody else? Is anybody left? If I don't know, if maybe one or two more confirm that you have opened it in a different. Done.
Yes, sir.
Okay. Okay. So let's look at the algorithm what we used for bar problems last time, right? So the first step was problem formulation. So the problem formulation required specifying nodes, elements, and boundary conditions, loads, and the AE. In this case, it will be for beams, it is EI, the flexural rigidity. For axial force problems, it is the axial stiffness AE. And for beam problems, it is I instead of A. That's the only difference. So let us start with that. Now, for example, let us take this cantilever beam problem. So for a cantilever beam, it is tip deflection is PL cubed by 3I. But let us see, can we code it and get the same answer? We should get the same answer, right? So let us start with the cantilever beam problem. Oh, I closed it. So first step is translating the physical problem to a finite element. Finite element setting. So you have, why does it do these changes? Yeah. So you have this. This is a physical problem. So the length is L, cross section EI, load P is applied. So I'm going to model it as a two-noded beam element like this. Okay. So it has got node 1 and node 2. Now again, one by one, one of you can tell me what will be the nodes matrix for this? Yeah, one of you can tell me the nodes, then somebody else has to tell.
0
Yeah.
and L.
0 and L, perfect. And another person tell me the elements matrix. How many elements we have?
One element.
One element. And what are the nodes? Like what is the, for the first element, what are the nodes connected?
1 and 2.
1 and 2. Okay. So in Python format, you can say it is 0 and 1 because numbering starts with 0. So this is the elements matrix. Next, what do we need? Boundary. What are the boundary conditions? Where are the boundary conditions applied?
0.
0. Okay. But okay, we'll come to the boundary conditions a little later. There is something there. Okay, so this is fine. Nodes and elements are fine. Boundary conditions will come a little later. Because at every node, you can have two kinds of boundary conditions, right? So let us specify the nodes first. So the nodes are 0 and L. So let me put L also as 1. L is 1. Charge my. Yeah. Let's take L as 1. So nodes matrix is 0, comma L. And the elements matrix is matrix of the first element's first node, which is 0 and 1. Perfect. Now coming to boundary conditions, you can have at every node you have 2 degrees of freedom, right? At every node we have 2 degrees of freedom. So let us say for node 1, let me define the boundary condition matrix this way, right? So let it be like at node 1, I am restraining the displacements as well as rotations. So it's like let me use 0 if restrained and 1 if free. Okay, you can, this is just a notation for the computer to read. We have some notation. Okay, you can also do it some 0 if free and 1 if restrained. That's not a matter. So yeah, 1 if free. So what I'm trying to say is, let's take so let me give the boundary condition as a table where the first one is node number. Then the second one is the value of displacement at that node and the rotation at that node. Right. So let me do this. Now, okay, so we can do this. So for the so yeah, now somebody can tell me the boundary conditions matrix. So what is it? Yes.
0, 0, 1,
Yes.
1, 1.
Okay. So when both are ones, you don't need to specify that, right? So it's actually free, but it's okay. This doesn't make any mistake. So okay, fine. We can do this. So this is okay, but this is basically meaning that you don't need to do anything here. So that's okay. Let's do this. So boundary nodes is so you only list the nodes where at least one of the displacements is restrained. Otherwise, there's no point, right? You can say it is in node 0, v1 is 0 and theta 1 is 0. You can say in node 1, v1 is not, sorry, v1 is 0 and theta1 is 0. And you can say in node 1, B1 is not restrained and theta1 is not restrained, but that's not really required. When that node number doesn't appear in the bound nodes matrix, you just ignore it, right? That's okay. Then what about the force matrix? So okay, until this point it's fine. Force and this one will come later. Now second thing, second step, initializing. Initialize global stiffness matrix. So what should be the size of the global stiffness matrix? First thing, what is the degree of freedom matrix for this problem? We have two nodes. So V1 theta 1, V2 theta 2. So it is 4 cross 1. Similarly, you have 4 forces. So the size of the global stiffness matrix is what? It is
10 cross 4 cross 4, sir.
4 cross 4. So this makes it somewhat different than the bar problem. Right? So you have a 4 cross 4 matrix. So every two pairs of entries are corresponding to one node. So this is one node, this is one node, this is one node. Like this. This is node 1. This is node 1 related to node 2. This is node 2 related to node 1. This is node 2 related to node 2. So here you have to assemble in a slightly different manner, but it's not very difficult. Okay, so let us say, so corresponding to these degrees of freedom, we'll see what are the, so you initialize the force matrix as 0, 0, 0, 0. So it is like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. What, so if you have n nodes and 2 degree of freedom per node, the total number of degrees of freedom is 2 times n nodes, number of nodes, right? 2 times number of nodes. So if you have two elements that are fixed, if you have two elements, then you have 2 degrees of freedom here, 2 degrees of freedom here, 2 degrees of freedom. So you have 3 into 2, it is 6 DOF system. Now if you have 5 elements, you have 10, if you have 1, 2, 3, 4, 5, 6. So you have, if you have 5 elements, you have 12 degrees of freedom. You have 12 degrees of freedom because you have 6 nodes. So the number of degrees of freedom for a beam problem are twice that of the number of nodes. Okay, so that's one thing. Therefore, let us start with initializing this, right? So F will come a little later on. We'll come to the force a little later. Okay, so we'll go to the assembly part. So the first part is, the first step of assembly part is, let us, we have to initialize, right? So initialize, how do we initialize? Yes, you can say K is equal to, or before even initializing, let us get the size of the matrix. So size K is equal to 2 times the number of nodes. But what is the number of nodes? Let us call that as something. Num nodes is equal to what? It is length of what? Length of nodes, right? So the nodes matrix gives the location of coordinate of every node. So there will be as many coordinates as there are nodes. Okay, so you can also code along with me. All of you can code along with me in the. Okay, I'm doing it in copy. It's fine. So okay, I'm doing it in the copy file. It's okay. So I get size of K is 2 times the number of nodes, right? Then what? Then I have to initialize K. So how do I make it 0? How do I get a matrix of zeros? Someone?
NP dot zeros of num underscore nodes.
Yeah.
Comma num underscore nodes.
Perfect. So this gives you a square matrix of size num nodes, comma num nodes. No, wait. Why should it be num nodes, comma num nodes? We just decided the size of k has to be 2 times that, right? So the size k, comma size k. So if you have 2 nodes, you have 4 degrees of freedom. So k should be 4 cross 4. And if you have 5 nodes, you need 10 degrees of freedom. So it is 10 cross 10. So you are doing this. Okay, we have initialized k. Then what do we do? Just similar to the bar problem. You can tell me.
For I
For
in range of
len of. We are looping over what? We are looping
nodes.
Elements. Loop, we are taking an element and we'll see where it will fit in, right? We are not taking a node. Yeah. Remember that we are going through every element. We are looking at the local node of element, that element. Then you're looking at local node 2 of that element. Then you see where it will fit in from the elements matrix. That's what we are doing. So you have to be careful.
Node 1
Okay, so sorry.
Node 1 equal to
Yes, node 1 is equal to lms of
II and
yes.
In bracket 0.
Yes. So what this means? So if you're not comfortable, you can define something called current element. Current element is elements of II. So you're going to ith element, and in that ith element, you're seeing what is node 1. So it is current lm of 0. This is fine. Similarly, node 2 is the second node of current element. Okay, fine. Next, we have to find the length of the element, right? So what is the length of the element? It is
nodes of
node 2 minus
nodes of node 1.
nodes of node 1. Perfect. Very good. Next, what do we do? I and E are given by the flexural rigidity and E are given by the code. Okay, then what do? We have to form the element stiffness matrix, right? So what do? We have to call, let's say small k is equal to, what did I call this function? Beam stiffness. So let it is, beam stiffness of what all goes into it? A, E, and it's not A, it's I. It's I, E, and L. Okay, now what should be our beam stiffness matrix? So let us say K is equal to, we know this already, right? It is, let me just first make the, okay, you people tell me, what should I write here? So what should be the beam element stiffness matrix?
EI by L cube, that is EI divided
E star I divided by
L
L,
cube.
L star star 3. Yes, perfect. Multiplying.
What, for 2 cross 2 matrix.
Why is it a 2 cross 2 matrix? This is a beam stiffness matrix, right?
Yes, right.
Yeah, so we just derived the beam stiffness matrix, right? It is somewhere here, right? This is the beam stiffness matrix.
Yes.
So it is 4 cross 4, right? So so how do I define a matrix in Python? np dot array. Okay, now let's start filling in the matrix. So you can read out the entries. So first row is, oh, you don't have the 12, yeah. 6 star L. Okay, I didn't share the, I shared, no, I didn't share this part, right? Yeah, it is 12, 6L, minus 12, 6L. Then this has to be symmetric. So this first term will be 6L. Then I think it is
Minus
4L. No, it cannot be minus. That's a diagonal entry. So it's usually positive. So it's 4L square. Yeah, I should have shared it, but it's fine. 4L square. Then I'll do one thing. I'll put it in split screen. Yeah. 4L square minus 6L.
minus 6L, 2L square.
2L square. Then the third row is minus 12 minus 6 star L. 12 minus 6L. Then the last row is 6L, 2L square minus 6L, 4L square. Okay, so this is the stiffness matrix. Yeah, you type it in your code without any mistakes. If you want, I can zoom it in, because if this goes wrong, every element will be wrong. You're looping it over all the elements. So type it without any mistakes in your code, then we'll proceed. Then you just return K. Tell me once you have typed, because this is you have 16 entries. They should be correct. So do it then. Is it done?
Yes, sir.
Done,
Okay.
sir.
Okay, good. So we got the now this will return the local stiffness matrix or the element stiffness matrix. Now, what was the next step last time? We have to plug it in into, if you see the bar problem, where did we do here, right? Yeah, we did this step where we took the local element and plugged it into the correct place in the global, right? We had a global stiffness matrix, and that you're filling it with the local matrix numbers. So here also you will do the same logic. Okay, so here we'll do the same logic. So plugging it. So this is step number 3. Populate the global stiffness matrix. So so how do we do? Take an element. First step is take an element and look at its node 1 and node 2. Now, the global stiffness matrix of something is equal to the global stiffness matrix of something. Initially, it's all 0, so they'll get added up. In that place, you'll put local matrix. In the local matrix, you'll start from 1, 1, right? And this will go on up to k of 4, 4. Right? You do this. This is capital K. Yeah, this is capital K. Now, yeah, one of you can tell me the logic how we'll do it. So I will tell first. Let me tell you. For now we are solving the problem of just one beam, but in general you can have n number of beams connected like this. And this, when you split it up, you will have elements like this. You take this element, first node of this element goes to here. But this itself has got 2 degrees of freedom, right? So the first 2 degrees of freedom of the first element will go to the first 2 degrees of freedom of the node, global node. The second 2 degrees of freedom of the first element will go to this point. Similarly, the first 2 degrees of freedom of the second element will also go here. And these 2 degrees of freedom will go here. So this is the logic. So here there is a summation. For the middle shared node, there is a summation, which gets contributions from both the first element and the second element. Now, if you look at the full stiffness matrix, you have V1 theta 1, V2 theta 2, and so on, V3 theta 3 up to Vn theta n. So corresponding to every node, how many rows do we have? Corresponding to every node of the structure, how many degrees of freedom we have? How many rows in the stiffness matrix? 2. So these 2 are for the first node. These 2 are for the second node. So these 2 are for node 1. These 2 are for node 2. And this is for node n. So last time what we did was we did k of node 1 comma node 1 is k of node 1 comma node 1 plus k of 1 comma 1, something like that we did. But this time we can't do that because every node contributes. So how do we do it? If you take this system, for example, if you take the system of 3 bars, if you take the first element, in the first element, let me put small k of 1 comma 1 goes to where? Capital K of
0,
0 comma 0, but it's like node 1 comma node 1. So okay, let me put it this way. So if you take ith so if you take ith degree of freedom, what are the rows corresponding to it? What are the global rows corresponding to it? In Python notation. So if you take degree of freedom 0, if you take degree of freedom 0, the first two rows are for degree of freedom 0. So this corresponds to for degree of freedom 0. Sorry, if you take the node 0 has degree of freedoms 0 and 1. If you take node 1, it has degree of freedom what? So this is this is row 0, this is row 1, this is row 2, this is row 3. So node 1, which is the second node, has degrees of freedom 2 and 3. So node 2 has degrees of freedom 4 and 5. So what will be node i's degrees of freedom?
I plus 2.
Is it I plus 2? Because if you take third node, it will be 6 and 7. So is it I plus 2?
2n, comma, 2i, comma, I.
2i plus 1.
2i plus 1. Perfect. It's just 2i and the next one, right? 2i plus 1 is the just the following. So this is the logic. Perfect. Okay. So very good. So think of the operations now, right? We take local node 1. We take local node 1. Find its global node number. Let us call it j. And corresponding to j, you have 2 degrees of freedom, which is 2j and 2j plus 1. This is the logic, right? You take local node, find the global node number, and in that global node number, you get two rows, right? So that's the idea. Now you think about this logic. So in the local stiffness matrix, remember local, not the global one. So local stiffness matrix is of size 4 cross 4. In that row 0 and row 1 are for node 1. And row row 2 and row 3 are for node 2. So firstly, corresponding to node 0, what is the local node number? So let me put it this way. So let us say this is going to be the logic. This will not change. K of global something is equal to K global of something plus K local of something else. Locally, there are two nodes. In the bar problem, they are just 0 and 1. So we wrote just 2 lines, actually 2 cross 2, 4 lines for 0, 0, 0, 1, 1, 0, and 1, 1. Now in this case, what are the local node numbers? Local nodes go from I is equal to 1 to I equal to 0 and 1. Right? Local node numbers go from 0 and 1. But for every local node, we have two components. What are the two components? One is 2i, and
2i plus
2i plus 1. Perfect. Then
2i
2i
plus 1.
plus 1, 2i, and
2i plus 1, 2i.
2i plus 1, 2i plus 1. So it's very simple. Only thing is, instead of doing it from no, wait a minute. So you have 2i. So these are the 4. So this is one submatrix, right? So for this is the local stiffness matrix of size 4 cross 4. And if you take node 1 alone, it has got entries 0. It has got two degrees of freedom, and those 2 degrees of freedom. So this is the first 4 cross 4 submatrix. So this is this submatrix: 2i plus 1, 2i plus 1, 2i, and 2i plus 1, 2i plus 1. This is the first 4 submatrix. This submatrix has to go somewhere. Where will it go? So in place of I, so this I can be from I'll tell you. So this will go to 2 times node 1, comma 2 times node 1. Right? So what is node 1? Node 1 is the global node number corresponding to I. And I goes from and corresponding to 1. So look at this, right? So locally you have just 2 nodes, which is 0 and 1. 0 corresponds to some global node, which is j, and 1 corresponds to some other global node. Now for the 0, for every global node, there are 2 degrees of freedom, which is 2j and 2j plus 1. Now this is the logic. So k of 2 into node 1 and k comma 2 into node 1 will take this component. So let me use this symbol just to say that it will get added up, right? So so this symbol means this plus something. So if x tends to this symbol means this so if I say x, if I say y goes to x, if I say this way, it is equivalent to telling x equal to x plus y. So have this notation in mind. So in place of if so I goes from 0 to 1, right? And as I goes from 0 to 1, node number, the global node number corresponding to I. So k of 2 into node 1, comma 2 into node 1 will take local node of 2i, comma 2i. And k of 2 into node 1 plus 1 and 2 into node 1 will take k of 2i plus 1, comma 2i, and so on. The rest of it you can fill in, right? Now you can tell me as I write in the code, so that yeah, I don't have to write everything here, but I will write everything and I'll share the file later on, right? Since we don't have time, I'll do this. So now let us say let us call, let me put the comment. Let us call local node numbers as P and Q. Now I'm going to loop over P and Q. So for P in range, so what is the maximum P can go up to? P can take either 0 or 1. So, so P can take either 0 or 1. And so range will exclude the last number. So it is P in range 2. And Q in range 2. Okay, very good. Now let me call node 1 is equal to current element of P. So I'm getting, so first step is I'm getting the global node number. Get global node number. Okay. Next, node 2 is equal to, right. So I'm getting the global node numbers first. That's very good. Then what should I do? I have to plug in. So what is the logic?
Capital K of 2 times node 1, comma.
Okay, so the idea is did I initialize capital K? Yeah, I have initialized capital K. Capital K is the global stiffness matrix. K of 2 star node 1, comma 2 star node 1 is equal to.
Instead, we can use plus equal to measure.
Plus equal to, I'm not sure if it works in Python. If it works, it's fine. Plus equal to, okay.
Small k of p comma q 2 times
2 star P, comma 2 star. Wait a minute. 2 star P, comma 2 star Q. So this has to be node 2. not 1. I'll just check if plus equal to works. I know in C it works, but say
Sir, it works, sir.
it works. Okay, then it's fine. Then we'll just use plus equal to. Then it's fine. Okay, so then K of 2 star node 1.
No, comma 2 star node 1 plus equal to
No,
K of
comma 2 star node 2 plus 1. Right? So for node 1, so you want to do this for 2p 2q 2p 2q plus 1 2p plus 1 2q and 2p plus 1 2q plus 1, right?
Okay, sir.
Or wait. Let's just see. So yeah, p can go from 0 to 1. So you're doing for 0 and 0. Next you have to do for 0 1 1 0 and 1 1, right? And next when p becomes 1, it will do it for 2 2 2 3 3 3 2 and 3 3. So that will finish the process. So now we have done for 0 0. Now let's do it for 0 1. So we are going to 2 star node 2 plus 1 plus equal to, yes, now what will happen here?
Small K of
Mm.
2p, comma 2q plus 1.
Yes. Next, let us take 2 star
Capital
ah,
node 1 plus 1, comma 2 times node 2 plus equal to small k of 2p plus 1, comma 2q.
okay, and capital K
Then
of
2 star node 1 plus 1 and 2 star node 2 plus 2 plus 1 plus equal to
small k
small
of
k 2 star node p plus 1, comma 2q plus 1.
okay. So this in one step it will fill in 4 values. So this is like 2 cross 2. So it will fill it in 4 steps. In 4 steps you will get 16 values filled in. So I guess I don't see anything wrong here. I hope this works. Right? This should work. Next, what do we do? So this will get the global stiffness matrix. Let us first check if it's giving the correct values. In this case, what should we get? We should get L, A, L, I, E, everything is 1. So you get 12, 6 minus 12, 6. We should recover this actually. Should actually recover this. Now, let me run this. We run up to, let's run up to this point. So we filled in AE, L elements, boundary nodes. Force we are yet to do, but I think we can run up to this point. So run. Okay, this is fine. This is not important. Now let me print K. What is it? Print K. None. Okay. Okay, we'll see what the issue is. Let's print it here, then we'll. Oh, I didn't return K. So it has to return. So we have assembled it, but it doesn't return anything. So this function has to return K. That's the issue. Return K. Just return outside. Right, so you just add this, in case you have written it, just add this return K, then we'll run everything. Yeah, so it gives what we expect, 12, 6 minus 12, 6, 6, 4, 6 minus 6, 2, and so on. So this is fine. The logic is actually working. Next step is to enforce the boundary conditions. Sorry. You can close this C2, it's not required anymore. Our next step is to enforce the boundary conditions. Before that, we need to get the boundary conditions. So this is the boundary nodes, right? Now let us construct boundary conditions. So let me call a matrix BC, which is like corresponding to every, or let's do one thing. Let's just take, let's go to this function, enforce boundary conditions, right? So you remember what we have in boundary nodes? We have, what do we have in boundary nodes? We have node number, first degree of freedom, second degree of freedom. So now you loop over all the boundary nodes. So what should I write here? For some JJ.
In range of.
So there is a shortcut to this. You can just say for I node, or you just say for I node in, because every node in that boundary nodes is it's actually a nodal information, right? So it's just say boundary for I node in bound nodes. So if you say I node in bound nodes, it will return one row of the boundary nodes matrix at a time. Now what is I node of 1? Let's say node num is equal to I node of 1, 0. Okay, then second disp, let's say disp d of displacement degree of freedom is what? It is I node of are you getting it? Is there any issue? Is there any issue understanding what I node is?
It's just a variable, no, sir.
Yeah, it is just a variable. So in the first iteration, it will give the first row in bound nodes matrix. In the second iteration, it will have the value of the second row in bound nodes matrix. So what I did is, instead of writing it as range of length of bound nodes, and then taking every row at a time, I'm just taking row at a time directly. So this is a Python shortcut. Rather than the other, let's say in C++ or Fortran, you don't have this, but here you can just take a row. So I node is basically this one entry. So in the first time it will show 0, 0, 0. In the second time it will give the second row, but we don't have a second row. That's how it does. So I node of 0 will be the first element in this row, which is 0. I node of 1 will be the second element, which is 1. And I node of 2 will be the third element, which is 0. So what is the displacement degree of freedom? What did we assume? We said it is node number, displacement, and rotation at a node, right?
One,
Yeah,
sir.
I node of 1. And let me say rotation degree of freedom is what? It is I node of
2.
Now this is one understanding. Okay. Now corresponding to the node number, what are the displacement degrees of freedom in the global stiffness matrix? So K of, now I have to set one row equal to 0, right? If the displacement degree of 0, let me say if the displacement degree of freedom is 0, then what I should do? I should make the corresponding row in the global stiffness matrix as 0, right?
Yes, sir.
What is the corresponding row in the global stiffness matrix? K of
0, colon, comma 0.
no, it is something comma colon, which is all columns in a certain row. What is the row number? Or let me also make row number. What is the row number? Or row ID? What is row ID? So some row will become 0. It will become 0. And K of row ID, comma row ID will be what? The diagonal entry will be what?
1, sir.
1. So this is fine. But what is the row ID? That is the important part.
0,
And
sir.
similarly, no, what is 0? Like, why should it be 0? I can choose to put fix the second degree of freedom and allow the first one, right? I can apply the forces on the first node and fix the second degree of freedom. Why should row ID be 0? Row ID is related to the node number. How is it related to the node number? Now, for example, if you look at this problem, I have, if I put it with 1, 2, 3, 4, 5, this has got 5 nodes. And here I am restraining the displacement degree of freedom. So if I just type row ID equal to 0 here, it will always make the first degree of freedom 0, which is wrong, right? Here, I want something to be 0 here, not here. So how do you...
Displacement degree of freedom. Displacement underscore.
But displacement underscore degree of freedom can take only 2 values, which is 0 or 1. In fact, let me do one thing. I'll make these two as just true or false. So here, if it is restrained, it takes a value true. And if it is not restrained, it takes a value false. So if some condition is true means, so if I just say if displacement degree of freedom. So if it is true, something has to happen. Now, my question is, what are the degrees of freedom corresponding to node number? So it's just as we did. So corresponding to ith, corresponding to global node J, the displacement degree of freedom is
2J.
2J. And rotational degree of freedom is 2J plus 1. So now I'm looking at the node, which is node number. The global node number is node number. Now corresponding to that, if displacement degree of freedom is restrained, which row I should make it 0? It is 2 times node number. Right. Now if this is one condition, what if rotational degree of freedom is restrained? If rotational degree of freedom is restrained, then what is the row ID?
2 times node number plus 1.
And these two conditions are the same. Okay. Yeah, of course, force also you should make it 0. So f of row ID 0. We are finding the force, so it's not a big issue. So this it will do, and it will return what? It will return K and F. Return K and F. Sorry, capital F. Okay, so we have enforced the boundary conditions. So what it will return? Capital K and F is equal to enforce boundary conditions of K, F, and what it is? Bound nodes. Oh, it's actually there. I didn't have to type bound nodes. So yeah, it's actually here. I didn't have to type. Okay. Then the last step is just solution. I'm reusing the same code. Right. I'm just reusing the same code. np.leanalgebra.solve this. Now only task that is left is to give the force matrix. So forces are also arranged in this manner, right? So in node 1, what are the forces? Applied forces in node 1.
F2 and M2.
No, why in node 1, F2 and M2? No, in node 1 it's always just F1 and M1, right? So this is node 1. There's nothing applied there. So what is F1?
0, sir.
Yeah, F1 is 0. What is M1?
0. 0, sir.
Okay, what is F2? What is F2 here? Here F2, there is a force of P applied downwards. So F2 is
P minus P.
minus P, and M2 is 0. We don't apply any concentrated moment. Now let me just define P as some, maybe I'll make it as 10, right? Just to be, let's make P as 10. So we have everything we can directly solve, right? So now let's print K and U. Let's print K and U. So I'm running it. Let's see how it. Okay, why does it take so long? Let me reload the. Enforce boundary conditions. There is some error here. What it is?
So the true have we connect
Sorry.
we have given true comma true. The true for the if condition and the true, are they connected?
Yeah. So what happens is it will say what we have said, what displacement degree of freedom is. So corresponding to that, if this means this is taken as this is coming from boundary nodes. So that's not a problem. It will be enforced. But the problem is not that. It says here list indices must be integer slices, not tuple. Okay, so F is the problem. So F has to be np dot array. That's the issue. We didn't make it a numpy array. That caused the issue. Okay, now it will be fine. Now let me run this. Run all. Okay. Too many indices for array. Okay. Okay. So F is a 1D array, so we cannot have this. It's just F of row ID. There's no column. It's just row ID. Now let's run. It should run this time. Now F is a column vector, so it cannot have any multiple columns. So this is the displacement and this is the rotation. So you can check PL cube by 3 EI. P is 10, L and EI are 1. So 10 by 3 is 3.333. So it has got a downward displacement of 3.333. And it has got a counter clockwise rotation of 5. So you know that it is PL square by 2 EI. The rotation is PL square by 2 EI. So P is 10, everything else is 1. So 10 by 2 is minus 5. And the minus denotes that it is a clockwise rotation. So we have solved this problem with just one element. But what happens if you use, now the code is not going to change. You can use the same code, but what happens if you use 4 elements over the span, right? Now, where all the nodes will be, you can tell me quickly. It's not going to take much time. So where will the nodes be? 0.
L
So,
and 2L.
no. We're using 4 elements. So I'm saying you will have nodes like this. The total length is L, and I'm using 4 elements. So 0. Where is this node situated? It's not so
0.25.
difficult. L back. Yeah. So you get the idea. So now tell me the node locations. 0,
0.25, 0.5, 0.75.
0.25 L, or let me just put L by 4, L by 4, L by 2,
L by
3L
3 by
by 4,
4 L.
and L. And what is the element connectivity? We have 4 nodes. So we have what is the element connectivity? You can tell me. First element connects 0, 1, then
2, 3.
no, 1, 2.
1, 2, 2, 3, 3, 4.
Yeah. So these are the 4 elements. Yes. AE, EI can be still 1. What is this AE? It's I. It's I and E. IE can still be 1. This is all fine. Now force, you can have the same force. We should get the same answer. Just because we use 4 different elements, we shouldn't get a different answer. So we have 4 different elements. Force is the same. Now what is the force array? Degree of freedom 0, 0. So which degree of freedom you will have force? It's here. So what is the degree of freedom here? What is the degree of freedom number? In
8,
Python.
sir.
In Python format, it is 8. So it is 0, 1, 2, 3, 4, 5, 6, 7, 8. 8 in Python format. So everywhere else it is 0. Let us fill it in 0, 0, 0, 0. Or I don't have to do this. I can just say f is equal to np dot array. What is the size? Or np dot zeros of, first I'll fill it with zeros of size 8, right? Of size 9 actually. Sorry, 10. Size is 10. Size is not so it has got 5 nodes, so 2 degrees of freedom per node. Now f of 8 comma 8 is 1, 10. Sorry, it's minus p. That's okay, right? And first, instead of typing all the zeros, I'm just filling f with zeros first. So this is fill f with zeros first, then modify one entry. Now nothing else will change. We have already coded the difficult part, so we have encoded everything else. So we just change this and run. You don't even have to run the previous part. So we run this. Now let me print. No need to print k. K will be very big. I'll print just u. So it is 0, 0, something, something, something. Now look at the last number, last things, right? So this means this is the displacement at the tip of the cantilever. So it shouldn't matter how many elements you are using. You can use 10 elements, you can use 100 elements, you can use 1 element. You should get the same because the beam finite element is exact as long as you have only concentrated forces. Okay, actually this is I. It's a problem. It's EI. Yeah. So as long as you have only concentrated forces, the beam finite element or the beam element should return exact values. Therefore, now also you are getting this PL cube by 3EI and PL square by 2EI, right? And intermediate values, wherever you have a node, you can get the intermediate displacement and rotation values. Okay, so these are all the intermediate values. This is the displacement and rotation at node 2, this is the displacement rotation at node 3, this is the displacement rotation at node 4. Now this is fine. So now can you solve this problem? The second problem, this is also simple. How many elements we need here? So let me, I'll give you some other problem as homework. So this you can solve directly. So how many, should I put a node here?
Yes, sir.
Yeah, because I'm having a force applied there. So I want to be able to put. So how many nodes are there?
5 nodes.
5 nodes.
5 nodes. And where are they located?
L.
No, 0.
0, L, 3 by 2, 3L by 2.
Yes. 2L and 3L, right? So this is L from this side. Total length is 3L. So this is L from this side. So this is these are the nodes, and elements are just the same. Elements are just 0, 1, 1, 2, 2, 3, and so on. And 3, 4. Yeah, 3, 4. And what are the boundary conditions? Okay, we'll do it right. So EI is this. Nodes are 0, L. L will take it as 1. And this is 3L by 2. Then you have a 2L.
3L.
And you have 3L. So this is the benefit of doing this coding. You don't have to solve a different problem every time. Just change the input you get. You can solve any boundary condition, any loading. So what are the elements? Same thing. Element connectivity is not going to change. It is the same. 0, 1, 1, 2, 2, 3, and 3, 4. Now tell me the boundary conditions. I'll put it in split screen so you can tell me the boundary conditions. I'll erase it. So first, what are all the boundary conditions? At node, yeah, you tell me. What are all the boundary conditions?
0, 1.
That is basically what do you mean? In node number 0, displacement is
Not allowed.
so it is true. Displacement is restrained. So if it is true means I'll put that also in comment. So here true means restrained. False means free. So in node 0, that is the first node, displacement restraint is true. Rotation restraint is
False.
yes. Then what about second? Yeah, now you can tell me. What are the other conditions?
1, false, true.
Why is it false, true? This is this node 1 in Python format.
No, sir. No, sir. 1, true, true.
Okay, why is it true, true? Why do you feel rotation is restrained? At this point,
Not
you can have some slope, right? Why should it be 0?
Need not be, sir. False.
Yeah, false. Then
The same. 2, true, false. And then.
which node is it? Which node is it?
Oh, no. It is 2,
2,
false, true.
What is true? You does 2 have a rotation restraint?
No, sir.
Yeah. So why is it false, true? It is just false, false, right?
Yes, sir.
Yeah. So basically, you look at the node. In fact, if it's false, false, you don't need to put it in bound nodes, but it's still okay. No problem. It will not get enforced because we are having 2 ifs. Only if at least one of the ifs is satisfied, we get this. So you can put it, but it's waste. But it's okay. In the initial portion, when you're just starting to learn, it's okay to include it. So look at it. In node 1, what do we have? It is displacement restraint, rotation free. Node 2, displacement 0, rotation can be non-zero. In node 3, displacement is not 0, rotation can also be non-zero. Although when you solve this problem due to symmetry, rotation will turn out to be 0. But that is after solving the problem. Before solving the problem, if I have if the load is acting at, if there's a moment here in addition to the load, or I have load somewhere else, you don't know the rotation here. So rotation is not restrained. Then what are the other conditions?
3, true, false.
3, true, false. And then last one is 4,
True,
what is it at
false.
notes? True, false.
True, false.
Yes. So that is it. Yeah, so P you can still take it as 10. And this as it is, if you see, it is statically indeterminate to the second degree. It's not easy to solve, but this you can get the solution in one step. So you print okay, we get junk basically. There is some 10 power 15 that is coming in. So oh, right, F is wrong. So what is okay, this is fine. Where are we applying F? T is applied where? So let's delete this. This can be causing some
6.
trouble. 6, right? 0, 1, 2, 3. No, it's not 6. It is 0, 1,
5.
2, 3, 4, not 6. P is applied at, so this node has 0, 1. This has 2, 3, and it's applied at 4. Right? So F is applied at 4. Other things are fine. I think EI can be taken as 1. L is 1 is fine. Others should be okay. Solve it and then print. Still there is some junk. Let's see K. K is fine. K seems okay. So it has to be diagonally dominant. So you get 6, 4, 6, 2. This 108 where it is. Oh, K is fine. K is actually fine. Okay, what is the size of K? We'll say K dot. Sorry. 10 cross 10. That is also fine. We have 5 nodes and 10 cross 10. That's okay. Yeah, we are not supposed to get values like this junk. K, F is fine. Okay, maybe the realistic values of I and this one will help. Okay, we'll do one thing. You can I will share the, if there is any issue with the implementation, I will check it with the analytical solution. I'll check with the structural analysis solution for this. So this can be solved as just a half problem. So it's just indeterminate to 1 degree, right? You replace this with a guided roller and make this a redundant, and this can be solved with that. Then let us check the analytical solution. If whatever values are getting, it cannot be 10 power 16. This has some flaw in it, right? This has got some issues. It may be because you're taking unrealistic values of E and I. So somehow K seems fine. K and F is also fine. So let's print this. Yeah, so these are the element stiffness matrices. So this is L by 2. So everywhere you have L by 2, you get you will get a cube multiplying it. So it will become 96. That's okay. 96 plus 12, 108. That's fine. I think implementation there's no issue, but maybe it's just that the values are very unrealistic. So assemble is fine. Okay, let us see this, right? We'll fix this, and I'll share the code, and I'll also share the manual solution for this. So they will match, no problem. They'll actually match. Then we can look at. Oh, right. This is the issue. No, that's also fine. F is NP0 is 10. Okay, then we can look at. Okay, let's see what F is. Okay, so I think today we can end it here. This is almost, we're already we've taken extra time. So next session we can look at trusses and frames, and that will complete the first 2 modules. That can be done faster because once we have, so beam and frame stiffness matrices are very close. You just have to add 2 rows and do a transformation. We can do that. And that solution is also going to be same. So hereafter, the conceptual part of the matrix analysis is gone. So we will not be deriving any more stiffness matrices. Only for the bar and beam we had to do it. For frame, it is just transformation. So we don't have to do that. Then we'll quickly get into the nonlinear part. So we'll start with just two bar problem in nonlinearity. Then we'll see what are the different ways to solve it. So one thing will be the iterative solution. We'll take small steps and then we'll get the full solution. Then finally, we'll incorporate the nonlinear solver into this finite element, this framework, right? We have this, right now we have this framework which we'll be reusing for everything. We have this, steps are only 4: element stiffness, assemble global stiffness, enforce boundary conditions, and then solve. In this, there'll be one additional step where we are doing some iterations to get the correct solution. So one more step will get added to it in the nonlinear problems, and those will get incorporated into this beam, frame, and bar problems. So basically, that will be the end of it. I'm sure the procedure is right. Maybe the numbers are just unrealistic so that we get these very large displacement values. But it's okay. I think I'll post the right solution onto this one. I'll run it with some realistic numbers and we'll see the solution. So
Okay.
So any other doubts you can ask me. I'm sorry I've taken too much extra time, but if you have any doubts you can ask me, and if not we can end the session. I'll post the code. I'll post this code. Because the changes are not saved in the classroom because I edited this copied file. So, and I also post the slides for this module as well as the next module. Yeah, if you have any doubts, you can ask.
Okay.
Otherwise, we can. Yeah.
Okay, sir. We will meet tomorrow morning, no, sir.
Yeah. We'll meet tomorrow. Yes. Yeah, today
Thank
I
you,
was.
sir.
Yeah.
Thank you, sir.
Yeah. Thank you.